Good day, my name is Ken Hill. Some apprentices know me as Big Daddy K, and I'm here today to show you DC generators. I'm not too sure if this head cam is going to work too good. Works good for hunting somewhat, but it's the best I could do. So what we're here to do today is we're going to basically connect a separately excited shunt generator and see what its effects are. Here's kind of my wiring diagram, and I got about 125 volts DC there. And here's my light board, here's my A1 and A2. We're going to hopefully have it generate clockwise rotation, so A2 should be positive. And we always need to maintain this F1 as positive. You notice that we don't use the series here, because in my other schematic diagram here, you'll notice that I've installed some ammeters here, one in the field amps, a voltmeter called the shunt voltmeter in the field circuit. This is a separate DC source which I've supplied. Down here I have an ammeter in series with our load and also in series with our armature. It's pretty much the same thing. Down here, this is going to be ET, which is our terminal voltage at our load. That is represented by this voltmeter here, and here's my load current. Over here is my field current, and here is my shunt volts. I had to put a tin plate over our light loads due to the brightness and the glare into the camera, but I think we'll get the idea. As I increase these switches, I will increase load. You should see the light back there increase. Over here, I was going to use this for my load current, but it just seemed too far out of place from where everything else was. This here, though, is my shunt field rheostat. So this is basically the green marking right there. That controls my output voltage, as I will show you. So as we look up here, this is my separate DC source. It's running through a bus across here. Better plug that in. So now I'm going to have a positive charge into my synchronous motor. This is essentially my prime mover. This is going to move the shaft at a constant speed to give me a constant output voltage on my DC generator. So I do have it connected three-phase input power supply, but I also connected the DC here to M1 and M2. It basically has this breaker involved and the field discharge resistor, which basically gets switched in and out of the circuit as you change the motor from an induction type to a synchronous type, because that resistor is in the circuit when it's basically first started to basically break down that induced voltage into the rotor, so then you can inject your DC voltage to it. That's when you take the resistor out. So over here I'll show you some of the wiring. I basically brought my supply, my positive current in, my positive current out, and this goes basically down to my load. Here, that's that breaker switch. And the field discharge switch right there. So it's kind of a rundown of what you're looking at. When I look down here a bit more though, this is basically my F1, A2, A1. I'm not going to use those. And here's F2. This is connected to a separate supply voltage. This essentially is just connected to my ammeters and runs over to that light board. So when I demonstrate this for you, I've injected my 208 volts. Now I'm basically going to turn on my DC breaker and inject my DC. I'll probably bring this DC voltage in the rotor maybe about 90, 80. I have about 1.5, but we really don't matter about this. It's about this bus voltage is constant. That is essentially what my field is seeing right there, 130. I cannot change that voltage unless I had a variable voltage supply, which is usually the matter for different output voltage controls. Once I basically close this breaker here, here is my voltage there. Show you that it's working. This is coming off of here. I got it running over to here, so there's about 96 volts. and there's no current flow to my circuit because I have no lamps on at this time. But this is my rheostat right here now. So let's just get this under control. That is essentially right there, the shunt field rheostat. And what I'm doing is I'm controlling my magnetic forces into the armature. So right now, if I have a low output voltage, that means my terminal voltage is only about 93 volts. What do you think is going on in my shunt field rheostat? Is that a high resistance setting or a low resistance setting? It's pretty much, if you guessed it, a high resistance setting, which gives me the low amount of current through the field, which deflects a very low magnetic field to the armature. When I go over here and I take this percentage out, so now I'm at 0%, that's going to be zero resistance. So now I basically move this rheostat and bypass that whole resistor. Now I'm applying that full voltage to the field. I have about 140 volts there right now. That is my full output voltage at the terminal, because I am applying the full 130 to F1 and F2. So the only other thing, I'm going to get it up to full load. I got it up to 140. Now I'm going to start adding light bulbs. So there's one light bulb. Did you see the voltage went down a bit? I'm going to turn on a second light bulb. The voltage went down a little more, no? Third light bulb. Voltage goes down more. Fourth. And fifth. Did you notice that the current was going up too? I'll take two loads off. When I start adding two more loads, the current goes up and the voltage drops. Essentially what's happening here is I'm putting more current through my armature, which increases more voltage drop into that armature, taking away voltage from our terminal voltage. That is essentially explained in your math as E terminal is equal to EG subtract IA RA. This is for generators, no? This is essentially a voltage drop calculation of the armature. So if current goes up, voltage drop goes up. So yes, as you can see, those lights are very bright. So I couldn't really increase my output voltage anymore. But now when I have full load, if I go back to putting this in a high resistance setting, do I not drop more output voltage? Because before, when I had them all off, I had about 96 volts there when I had this rheostat to full resistance. And you'll notice the lights aren't as bright. Get more voltage, more current flow, right? So you should see that in there. And also when I adjust my field, am I not adjusting the current? I'm adjusting my output voltage and my field current. So it's basically all interrelated. So that's my full output voltage again, is 116. This is what we would use for our calculations. So if I had 116 at full load, now my no load is about 138. So there is some math that should establish these for you. And yeah, I guess that's about it. But the next one we're going to do is going to be a self-excited DC shunt generator. Thank you for your time and have a good day.